How's it going, guys? And welcome to part 3 of building NanoChat from scratch. And in last video, we did the regex tokenizer. So feel free to watch that if you haven't already. And now, in this step, we'll be implementing half of the NanoChat tokenizer as it is in the NanoChat repository itself. And in particular, we'll be implementing these methods. So let's just read them one by one. We'll be making the init method, which initializes a NanoChat tokenizer object with a TikTok encoding and a beginning of string token string, and it stores both while caching the BOS token ID, which we'll talk about why we cache that when we get there. And then we have a train from iterator, which takes a NanoChat class object, a text to train on, and a vocab size, and it trains a tokenizer from the text iterator and converts it to a ticktoken.encoding object, and returning that as the return. Then we have a encode special, which is a cache wrapper around ticktoken's method for efficient encoding of special tokens. Then we have this one, which is just a getter method, so I'm just going to skip it. We have encode, which encodes in the ticktoken with the ticktoken method in essence, and prepends /appends based on your special tokens, the special tokens that are required, and then decode, which is just a decode function, of course. So one thing worth noting is that the special tokens are added when creating the ticktoken.encoding object, not during Python training, which means it's essentially abstracted for our purposes. But if you were to not use ticktoken, then it is necessary to implement all of the logic required for handling special tokens. So in the repository of this tutorial, there is a special tokens.py, and I will take the next maybe 2 minutes to go through what this represents, because this is explaining how one would go about implementing special token handling. So in our init method, first of all, we have two dictionaries that we must initialize, one being from special tokens to their integer, and then another being from the special token integer to the special token string. And just as we have the self.merges and self.vocabulary, which are in some sense inverses of one another, we also require these to retrieve our special tokens in separate methods. And then we have a register special tokens method, which should actually be called in, okay, we're calling it outside of the function, but it could also be called an init method, so that's fine. And this is just populating the inverse special tokens dictionary, since, well, we need both forward and backwards, and the input to special tokens is just the dictionary itself. So we don't need to do any special logic or manipulation on that. And you can see that the special tokens dictionary would look like this. We'd have end text token with the index 100,257. And then we would just inverse that in this dictionary here. One thing that is worth noting is that special tokens must have IDs greater than or equal to vocab size, which is to say that you have your max vocab size that you train on, and then you add above that threshold for all of the special tokens, because you don't have overlapping IDs, of course. IDs are unique. And then what is actually changing in the train method? You just need to reserve space for special tokens. So let's say that in this example, you plan to add 8 special tokens later, then you do 8 fewer merges. So the number of special tokens is the length of the special tokens dictionary. This is quite standard. And you can also just handle for no special tokens by setting that to 0. And then the number of merges is equal to our vocab size minus 256, since we have those initial 256 bytes, which is the UTF-8 byte strings. And then we also have our special tokens, which is subtracted from the number of merges. So we have to have space for those special tokens once we add them at the end. And just now I realized that this is incorrect because it shouldn't be greater than or equal to vocab size, but it should be that special tokens plus the number of merges plus 256 should equal vocab size. And that is just it inversing this equation here. I think if I portrayed it like that, it would be slightly more intuitive, at least now that I'm thinking about it, it is for me. So you have this, and then you have this. So 256, the first base tokens, plus the number of special tokens, plus the number of merges, equals our vocab size. And because of that, I'll delete this. Okay, so that's all you have to change with training. Make sure you're not training over the token limit. And then we have our encode ordinary, which we did last video. So this is the same exact thing with our regex token splitting. But then we lastly have a encode and a decode, which are slightly advanced, I would say. But let's first look at encode special, which is just a encoder that is used to encode a single special token. So all this does, it goes into the special tokens dictionary and then returns that special token's ID. And if for some reason you call this without a special token, then it will raise an error. But as this is like an internal method, or at least for our intents and purposes it is, then it should never actually trigger this. So let's go to encode and see where it's used. So in the tick token standard, there are 3 different ways where you can call this encode, which would be, first of all, which is allowing all special tokens, none, ignoring special tokens, which means like if you have the BOS text, like this might be tokenized like this. Like this is the first one. Well, in reality, it wouldn't, because you would first split up the punctuation, right? So it would be probably tokenized like this into these 3 tokens, but you of course would not want to do this, right? They're called special tokens for a reason, so you don't encode them normally. You would just put none to ignore if you have like no special tokens in your text. But then if you want to have none and then raise an error if a special token is found, then you would do this. And this is the default and is also safest, because if for some reason you have a special token, but you have input a text which you believe has no special tokens, then you should raise an error if that's the case. And then that's, I think it went through all 3, so there you go. If allowed special equals none raised, then we'll go through every single special token, and if that special token is in the text, then we'll raise an error. So this is the first condition. Then if we say that there's no special tokens in the text, then we simply do encode ordinary, which just encodes the text as if there weren't any. And if we allow special tokens, then we will set allowed equal to the special tokens in our tokenizer, or like whatever we have initialized at this step. And the second to last condition, which I didn't mention here, is you can also just input a set, which only allows tokens in the set there. So if the instance of allowed special is a set, then we will set this to our special tokens here and proceed as normal. And then if none of the other conditions are met, then we just return a value error. Okay, so this is like determining which special tokens to allow in this logic. After this logic, we create a regex pattern to match any allowed special tokens, which means getting the keys from the special tokens dictionary, which is just equal to allowed. If we have allowed equal to all, then allowed just becomes the specials token dictionary. And then we will split that up. Now we have the logic for creating our list of encoded IDs. So for part and part, which is our regex splitted text, if the part is in allowed, meaning if this part is a special key, then we will take the allowed dictionary, which has our special key to value mapping, and then take the value, which will give us the ID of that special token, and add it to the IDs list. And then if not, we just will extend our ID dictionary by the encoding of this part using encode ordinary part. How come here we have append and here we have extend? It's because append will we only append one special token at a time at max, but here we could have theoretically like many tokens that we will add, so we need to do extend. There you go. And now let's see how come we need self.inverse.special tokens. And this is because of the decode. So we decode token IDs, handling both regular and special tokens. Let's first initialize a list, which will have our part bytes, which is then joined with a binary join, and then decoded using UTF-8. So this is all standard. Like the only thing that's changed is inside of this for loop. And one other thing here you can see is errors replace. If there is some decoding error, since we are dealing with special tokens, then you will just kind of replace ignore. I think this is what this keyword argument does for the decode. If it says here, then I'll tell you guys. So yeah, you could either have errors equals strict, which would propagate an error. Okay, and then other possible values are ignore and replace. So I think ignore is what we should have here, because replace would make me think that you need to supply some argument to replace it with. So I'm not sure why this is like this. So let's change it to ignore for now. And if anybody knows or wants to check, you can look at the difference between ignore and replace, but that's not too important here. So for our list of IDs, first of all, we'll say if the ID is in the self.vocabulary, this means it's a regular token. So we just get the ID from the vocabulary and add it. This is simple. And then if the IDX is in the self.inverse special tokens dictionary, which if we come back here, right here, we can see that this is from int to string, which is what we want, because when we decode, we get a list of integers. And in this case, we'll get the string and encode to bytes when we get the special string ID. So first of all, you get the special string, which gives you the string itself. And then we will add it to the parts byte by encoding it. So this is kind of strange, right? We're first encoding it to decode it. Like, why are you doing this reverse operation? But just because the regular tokens are in byte strings. So just to make everything simpler, we just encode this to a byte, and then we will decode it once again here. You could definitely do this more efficiently by just keeping this as the string itself, since you know you don't need to decode it. But it's just simpler if you encode it and then put it with everything else, and then decode it once again later. And then we'll raise the value error if there's anything weird. And then encode special once again is called. It's actually not called here. I just realized that because we already have the self.special tokens dictionary, which is kind of that function itself. As you can see, that function just calls that dictionary access. So if for every reason you want to encode a special token outside of the tokenizer, then you can by just invoking this. So it's not a private method, which I said that was incorrect. Okay, so now I think we're ready to talk about the topic of today's video. So that took more than 2 minutes. I think that's what I quoted myself as saying. And we'll reiterate quickly the principles of our series, which is that we're doing this together and we'll learn through problem solving. I write the pseudocode for each function before implementing it. We demonstrate everything through small examples, and we do this all through one take. This video I already failed. I'll have to split up some parts of the video since I kind of got confused when I was explaining the special tokens. If you noticed, there was 2 cuts, so sorry about that, guys. But let's first go and just copy paste our special tokens, which I have in my clipboard, because these are the special tokens used in the NanoChat repository. Actually, if we come right here, we can see that I just copy pasted it from this. So yeah, that's all we have. And if you notice, we have some things that you'll notice as something that you recognize, such as like beginning of sequence, user start, user end. We won't be using these anytime soon because this is all for conversations, and the tokenizer doesn't know what a conversation is. This is going to be implemented once we do our render conversation, which is going to be next video. So we have this, and then we also need 2 imports. So since we do use TikToken in this tokenizer for encoding, we need to import that for later use. And then also something that is going to help us cache. So I remembered, I mentioned cache at the very beginning of the video. So we import LRU cache, which stands for last recently used cache decorator. And this just makes our tokenizer more efficient, in particular for special tokens. But once again, we'll worry about that when we get there. And now we can finally make a new class, which is called the NanoChatTokenizer. And this is the last tokenizer class that we're making. This is going to be the one that we use for the rest of the series when we require our tokenizer for tokenizing. And what comes in our init method for this class? Well, it's going to be the tick token encoding, as well as the beginning of speech token. And for the encoding, we'll just establish that, we'll just set it to self.enc, like as a member. And then the beginning of speech token, we'll just call it the self.beginning of speech token, beginning of sequence, I always mix that up, sorry. ID equal to self.encode special, which doesn't exist yet, but it will. And what did we just do here? So first things first, we have a special status for the beginning of sequence token. And if you come here back to the NanoChat repository, we can see why. And it's because there are two different ways of calling the beginning of sequence, end of text token throughout standard implementations. And we use beginning of sequence, but let's see what Andrew Karpathy says. So tick token calls the special document delimiter token end of text. Yes, this is confusing because this token is almost always prepended, which means added at the end to the beginning of the document. Sorry, prepended means added to the front. Appended means added to the end. So that's why it's called beginning of sequence, because in reality we add it to the beginning. It is most often used to signal start of a new sequence to LLM during inference. So in NanoChat we call this beginning of sequence so that it's more semantically correct, but historically it's called end of text. And when we load a pre-trained tokenizer, which we're going to have the option of doing here, we will use end of text because that's how it's handled in those tokenizers. But if we train our own tokenizer, we're going to use beginning of sequence. And for this reason, we need a member of our tokenizer which stores the value, which essentially tells us whether we trained our own tokenizer or whether we loaded one, so that we don't use the wrong, what does he call it here? The wrong document delimiter token. So that's why we have this in particular, and the encoding which comes from tick token itself. This will once again be elucidated once we call tick token.encoding, which is the method that gives us the tick token tokenizer object. Okay, so we have the init method set up now. What's next? It's going to be train from iterator. So train from iterator, if we remember, is a method that trains a tokenizer from a text iterator and converts it to a tick token.encoding and returns a new instance. Okay, so let's go down and make that function now. So first thing first is this is going to be a class method because it returns a class object. And this also, I keep on saying I'm going to explain this at the end, but I'm sorry, I will be explaining this at the end. It's just more simple to elaborate when everything is in place. So what does this take? It takes a class object as opposed to a instance object. And this is just the standard way that class methods receive. So you can see here, it says it receives the class as implicit first argument, just like an instant method receives instance. To declare class method uses idiom. So that's like the high level overview. And we take a text that we train over, our vocab size and our regex pattern. And let's do the pseudocode. So first step is to train a Python tokenizer. And this is where Karpathy's repository trains a Rust tokenizer. So we're not doing that, as we already know. And then once we do this, we will convert. So all we really want here is self.merges. It's funny, we're going to use the regex tokenizer that we have here to train it and then throw it out. And why do I say throw it out? It's because self.merges is all we want and need from the tokenizer training. And everything else about the tokenizer, which is really just a vocab, like that's really all you get when you train a tokenizer, is discarded. So the object is discarded essentially, and we take these self.merges, and then we will convert self.merges to mergeable ranks, which is how this is how tick token stores its merges. And for the case of our self.merges, if you recall, let's come to where that's initialized or where it's created, because that shows you the semantics. So it's a mapping from self.merges, right? Self.merges is a mapping from pairs to indices. I think that's how you spell it. But that MR, which is mergeable ranks, is the opposite. That's all I'll say right now. And let me spell this properly. Okay. So this is the first two steps, and there's two more. Step 3 is, since we didn't use special tokens in our regex training, since it was done, or it will be done for us by tick token, we need to add special tokens, which is to say, just give the special tokens to the tick token call, but we need to give it an object in the argument. And then we, in step 4, will create and return the tick token, that's hard to spell, .encoding object. So those are all the steps. Let's just start off with step 1. And it's pretty simple. We do tokenizer equals regex tokenizer. We need to train a tokenizer, so we first have to initialize one with the pattern. So I'll just say pattern here. And do we have the pattern saved somewhere here? Let's see, because, okay, it's not actually saved anywhere. So I'll just steal this. Actually, we'll do that at the end. So since it is a argument of our method, then we don't need to set it for now. I just realized that. Sorry about that new move. Okay. And then we are doing the same vocab size, except, or the same calculation without calculating the size of our special tokens, because that must be considered, and minus len of special tokens. So here we can just call this kind of global object, since we initialized it or just printed it out here. So whatever our vocab size is, it will be subtracted by whatever 8 or 10, how many there are in the NanoChat library. Okay. And immediately we're going to assert that this vocab size is greater than or equal to 256. So we get our vocab size, subtract it by the number of special tokens, and then I want to see how many other 1, 2, 4, 6, 8. There's 9 special tokens. So we should have a vocab size that is at least 265 in order to train a tokenizer, or else we have less tokens than the 256, which is the base number of byte strings. And now that we've done our little check, we'll do tokenizer.train, and this is going to take our text, and it is going to take our vocab size, no special. Simple enough. After this, we're already on to step 2, and we're going to abstract this for now, because we're going to make the mergeable ranks helper function at the end, but we're just going to call this get. I have this in my clipboard, so let's just get it here, get mergeable ranks on the tokenizer. And I'll comment this out so it doesn't give us an error for now. And then after that, we're already on to step 3. So first of all, we need to calculate a tokens. Yeah, never mind. We're not going to comment that out because I need mergeable ranks for this step. We're going to calculate a tokens underscore offset. And what is that? This is just the number of tokens that we've merged, because we need to know, okay, what is the first special token ID going to be? And in order to do this, we need to calculate the number of mergeable ranks. So for now, I would just say treat mergeable ranks as similar to self.merges, except it's just stored in a different format. Okay, and then we will initialize our special token so we can feed it to the ticktoken.encoding class instantiation. So what are we doing here? Special tokens is going to give us a token and an ID, which starts at tokens offset and then is added by I. We're going to do a list comprehension here. And I'm just going to do this in 2 lines so that it's more legible. I don't know why this won't let me just get an I. It's because I haven't done this list comprehension yet. For I, comma, token in enumerate special tokens. There you go. Okay, so what have we just done here? We made a special tokens dictionary which maps from the special tokens to the ID, starting at tokens offset, which is the last merged token, and it's from the special tokens list here. Okay, and now we're already ready for step 4. So encoding, which is this object here that we're gonna initialize soon, is equal to a tick token dot encoding object. So it creates an encoding object, and we have the following arguments. Name is the name of the encoding. It should be clear from the name, etc., etc. We have our, okay, there's more than I'm actually going to use, but we have our special tokens as well. Where's mergeable ranks? We have our mergeable ranks is a dictionary mapping mergeable token bytes to their ranks. So that is that. And then we also have our pattern. So where's the pattern string? Okay, there's the pattern string. So let's put all that into this dictionary here. So, I mean, I'm just going to call it NanoChat. Have no other name to give it. Pat underscore string is going to equal pattern, which we get from there. And then mergeable ranks is going to be equal to mergeable ranks. Pretty standard stuff. And then lastly, special tokens is going to be equal to what we just made, which is called special tokens conveniently. And then we're going to return a class object given the encoding and given our special string, which is called the beginning of sequence string, because it needs to be saved in this member of the class object. So this is how a factory method works. It returns a class object, and then it will be initialized in the init method. So we never actually call the init method directly, which is kind of cool. That's how factory methods work. Okay, so we've done trade from iterator. What's next? Well, we have our encode function. So since we do have this encode special, let's just implement that first. And this will also allow me to explain why we have this strange LRU cache thing. So LRU cache is a function decorator, and we're just going to specify a max size equal to 32. And there you go. So what is actually happening here? As you can imagine, when we encode a special token, it's going to be the token that we use like essentially the most in our tokenizing process. And for this reason, if we cache the value of the encoded token, then we can just be much more efficient. So all this does, this function and decorator, is that if in the last 32 function calls we have encoded a specific special token, then it will no longer need to call our encoding method. It will just return it through the cache. But if it doesn't have it cached, then what we'll do is it will call our self.encoding object from tick token, encode single token, and text. So I think text here isn't the best name. I'll say Yeah, okay. I mean, I don't know what else you would call it than text, to be honest, because you're returning a token. But now at least we have this encode special set up. So it caches it, and we return that object either from here in this method or from the cache. And you may be wondering, okay, why, if we're using tick token, are we also calling a secondary encode special method? And this is once again because when we're handling special tokens, just as was the case here, we do want to have a separate encode method for special tokens. And whereas this one wasn't used in the encode setup here, this one will be used. So you'll see right now, because the next method that we're implementing is actually encode itself. So def encode. And what are the arguments? Of course, self text, because we're encoding some text. Prepend equals none. Append equals none. And then also they have number of threads, because if we're encoding a batch of text, then we can also do this in a multi-threaded situation. And this is just straight from the NanoChat repository. Okay. And the reason why you have prepend and append is because if you're doing beginning of sequence, BOS, then you want to prepend. If you're doing end of text, then you want to append, just so it makes semantic sense. Otherwise, it really isn't anything to like stress about. So if prepend is not none, then we will say our prepend ID, which should be end of text, which should be beginning of sequence. I keep on mixing them up, sorry. Equals prepend, which would just be the argument here. If is instance, if the prepend is an int, because we have an int ID when we tokenize something, and else we will do self.encode special. So we're calling self.encode special on prepend itself. That means it was not the ID, it was just the special token that we got. So this can handle both token inputs and just raw text inputs for the special tokens. And this will be kind of just the same thing for append. So let's just come here, come here, come here, come here, and come here. I think, shoot, I messed it up, guys. Sorry. I thought I could do a program remove there, and okay, it's working now. And kind of highlight them so that we could get them all in one. There you go. And I spelled the pen wrong. Well done. Okay, I think everything here is good, except for the fact that, oh no, everything is good. Okay, so this handles both append IDs and prepend IDs. Now, once again, the code from the NanoChat repository does have quite a bit of exception handling, just to make sure that we are giving it proper input. So we'll first check if the input is a string. And if that's the case, we will get our IDs, which is just the encoding using encode ordinary, which is a standard function in the tick token encoding class of the text. So we have our IDs now, and you might be like wondering, okay, why aren't there any special tokens? It's because we haven't added any special tokens, and by default, if there are special tokens in here, then it will raise an error anyways. That's the default parameter to encode ordinary. If you actually come here, okay, it's not giving us the function hint, so never mind. Okay, and then now if prepend is not none, then we will add it to the beginning of the IDs list. So IDs.insert. I think we do index first for a list. Okay, I hope so. And then the prepend ID. And then instead of doing that funny copy thing, I'll just say if append is not none, IDs.append, append ID. Okay, so now we've added these special IDs, and I just realized now this is not because of some strange exception handling. This is because this function can not only take a single string and encode it, but it can take a batch of strings. So elif is instance, or a list of strings, not a batch. Text list. Then we will say IDs equals self. Let's just copy paste this because there's a lot of similarity. And very conveniently, encode ordinary has a batch function. So we'll take this batch function and we also will specify the number of threads. Where's number of threads? There it is. And then we will do a for loop. So first of all here, for I in IDs, for every single text that we've, for every single text that is in the ID list, we will just insert it here. So this is how we add all of the IDs in a prepending way for a batch of text. And then we do the exact same thing here for, let's just call it something else so that we don't get mixed up. For J and IDs, we will do j.append, and we won't forget the colon. And since we do have this triple structure, we'll say else raise value error, invalid input, and we'll make this an F string so we can actually give the input of the text. Type of our text. Text type. Okay, so invalid input type, boom. And then now we return IDs. So there is your encode function, very nice. And now let's get this show on the road and finish up because this is taking too long, guys. We're going to just make our decode function. And luckily for us, it is an insanely easy function because it's return self.encode.decode of IDs. If I can spell right. Look at this, guys. Everything is handled in tick token. This is amazing. One last cool thing is def __ call __ self star args star quargs. Highlight this. What am I doing here? I am making it such that we forward the encode function to the object itself if we call a method on the object, which is to say that now, instead of having to do like NanoChatTokenizer.encode like this, we can just do NanoChatTokenizer like this, and this call will forward this function with these with like the star args and star quargs argument forwarding. This is standard in Python. So this is actually quite a cool method here, and we'll see it in action when we call the encode function on the method itself. And you can actually do this for many different functions in Python. So anything that's a double underscore is kind of the, I would say, like the behind the door set of methods which are implemented in the library by standard, but which you can change. So for example, there's the equality function, which will evaluate if two objects are the same. And for like the integer class in Python, this literally just does integer equality. And then there would also be like the, let's show you one more before we actually get on with the topic of the video. There's also the repr one, which will return you the representation of an object. So let's actually implement this so that we can see how it works. And I just think it's really cool, like learning opportunity. So we're going to do it anyways. And what this repr will return is just the name of the tokenizer. So it will say return self.enc.name. Hopefully this will work because we set the name here. I'm not sure if we have to put I don't think we have to do that because the name should just be an element of the class. So let's see if this works later on. And let me just double check if we've implemented everything. Init, train for editor, encode special, get beginning speech token ID, encode and decode. Okay, guys, well, this should be everything except mergeable ranks. So good thing I remember that. Let's implement mergeable ranks right away. So let's come here just above the class because it's not actually a class method. It just gives us a modified version of the self.merges dictionary. So it doesn't have any interaction with the NanoChatTokenizer class itself. You can make it a method of the tokenizer class, but I don't really care. We're not going to do that. The regex tokenizer class is what I meant. So let's just first make the dictionary itself, which is just empty, and this is going to give us the final result, or this is what we'll return in the final result. So before I forget, let me return it as well. And then now the function will be in between these two lines. So just as we have the base 256 byte strings in self.vocabulary, we need to add that here because the mergeable ranks doesn't have the first 256 IDs. So mergeable ranks of bytes of I always forget this. So it needs to be an iterator. So we need to make a list of I equals I. So this is saying that for like the byte 0, it has the ID of 0. And I'm sorry guys, I realized I didn't even talk about the pseudocode. So let me interrupt myself and show you guys what mergeable ranks is itself. Courtesy of Cursor, we have that mergeable ranks is the tick token vocabulary format, which is a dictionary of bytes to int. And for example, for the capital letter A, we store the byte string of A, which is this hexadecimal 41. And for the merged token, capital HE, this would just be the merged token 48 and 65. And then for the merged token LL, it would just be this string twice. So this is how it's stored in tick token for both encoding and decoding, and you convert your Python tokenizer merges dict into this format. So what is the format of this dictionary? If I get this out of the way, then I can show you by looking at how it was here. So merge is a list of integer pairs to IDs. So the only thing we have to change here is make these integers a byte string and then merge them together. So don't ask me why they did this. In my opinion, it's a worse way of storing these merge strings, but that's just how it's done. Let's look at what we've done so far. So we first add the base 256 string, since that was usually provided by vocabulary, but in this case we need to create it on our own. So for I in range 256, mergeable ranks bytes I for that specific byte string is equal to the index I. Okay, and the next step is to add merged tokens in the order they were made and with the bytes, not the int pairs, as this is the case in self merges. Just as a reminder, we don't want this. We want to merge those on the byte level. So because we need integers, because we have integers, we want to map those to bytes. We need to get a helper. Where's my function? Oh, there it is. Which I'll just call token bytes, which is a dictionary that maps from integers to bytes. And for this one, we will go ahead with the list compression. For I in range 256, we will have now a mapping of integers to bytes, which is very useful. Why is that? Because let's now iterate over self.merges. So for pair, comma ID in tokenizer.merges, we will do the following. And we want to change this to items. I forgot that it's stored as a dictionary. We will say that the merged bytes are equal to the token byte of pair 1, the first pair, plus token byte pair 2, which is the index 1. So first of all, that should be a plus. And second of all, since these are byte strings, we can add strings in Python. So it'll just add them and concatenate them. And we have the first pair here and the second pair. And we just get its byte by this dictionary lookup here. And then now, because previous merges can become merged in later merges, we need to add this to our token bytes so that it is up to date. It's staying up to date. So token bytes again stores integer for ID equals merge bytes. And then lastly, we can create our mergeable ranks for that entry, which would be a mapping from bytes to integers. So merge bytes, right? Merge underscore bytes equals the ID. And there you go. You have a mapping now from binary, not from binary, but from the byte string, not binary. There you go, to the ID. And yes, I was wondering if that was highlighted weird because it's a specific Python keyword. Yeah, maybe it is. So I'm not going to use that. I don't know why ID was highlighted in like extra bold. So let's just call this index, or let's just even go ahead and call this merged index. Okay, so now you have mergeable ranks. And finally, we should have everything such that we can train a tokenizer at the bottom of our function here. So if I come here and say tokenizer equals, I'm just gonna grab the regular expression string or everything at once from this other pane, and this is our text, our vocab size, and the regular expression string for tokenizing. And let's just see what happens if we go ahead and clear and then run our BPE in NanoChat. bp.py. Okay, no module named NanoChat. Where do I have this? Special underscore tokens. I don't know why that's there. That's strange. Okay, now let's run it again. All right, I think I have a problem here with the get mergeable ranks because I called it the wrong name. Okay, what line is this? Line 250. All right. Name get mergeable ranks is not. Oh, I spelled that wrong. I actually don't know which spelling is right, but we'll assume that it's that one. And now we have a result, which if we now come and first of all do tokenizer hello, so that I can show you guys that this call is essentially forwarding encode, so that we don't need to do encode. Or what I'll do in this case is come like this. I'll say equals this, and we'll see that it will hopefully give us the result of true. Okay, so these are the same. And then if we actually print this, what are we going to get? We're going to get something which should be tokenized. Boom. And the text here was, what was it? Okay, it was the Unicode text. I want to come and take the same text that was used for one of the tokenizers in the NanoChat repository, just so we have something different. So this is like a news article. And hello, I am so happy today. Let's see if anything here gets tokenized. Okay, so we have some IDs like 258, which was tokenized. Maybe that's the space S, I'm not sure. And let's just make sure that decoding works as well. So we're going to just take this, which I have, which takes our tokenizer, decodes the hello, and that gives us back hello. So everything's looking pretty good here. And now I'm just going to give you guys a quick summary of what we just did. So in this video, we made our NanoChat tokenizer, which is what we're going to use for the rest of the series. We gave it mergeable ranks, which is how TikToken takes its object and gives us a encoder output. Then we have the train from iterator, which gets an object from this specification and returns a TikToken encoding. We have encode and decode now working with TikToken encoding, which is much more efficient. It's implemented in C. And one other thing that I wanted to talk about, not only just mergeable ranks, but why we are using the class method in train from iterator. So I said it's because it's returning a class object, but if I want to motivate this slightly more, once again, it's called a factory method, and it returns a class object instance. And instead of calling it on an instance, you call it on the class, which you can see was done here. And I just lost it, so let me open up preview again. So why is this used instead of a regular method? It's because we don't have an instance yet, we need to create one first. The CLS refers to the class itself in the method when we return, so we can return a class object like that. And if we didn't use it, what would happen is that you'd first have to create an instance that was empty, called a dummy instance, and then train it. So instead of this class method lets you call it directly on the class to create an instant, which is cleaner. So you can see why we use class instance. And yeah, that's pretty much it for our video. In the next video, we'll be implementing these functions and the tokenizer will be completely done. And then we'll be ready to move on to the language model itself. So hope you enjoyed the video and I'll see you in episode 4.